Okay, welcome everyone. So it's a great pleasure to introduce you all to Shriram Krishnamurthi. He's a professor of computer science at Brown University, and there are two really interesting strands of his work, at least that I know of, right? So first, he's co-founder of the Bootstrap project, which integrates computing and data science into multiple subjects in the school curriculum. And Shriram, I don't know if you know this, but we actually presented that model to the NEP committee. And in some way, it has made it through to at least the maths curriculum, right? And we're following Tamil Nadu, which has already started this, right? The second interesting strand of his work, and I think we'll see elements of that in today's talk, is he's blended computing education and other sort of technical areas like programming language design in ways that I think are really, really remarkable. So he takes challenges from the education space, challenges in computing education, and then he develops technical solutions to those challenges. And then those solutions themselves sometimes, have impact way beyond computing education. And Racket is an excellent example of that. So he's received many, many awards. Just a few: SIGPlan Robin Milner Young Researcher Award, SIGSoft Influential Educator Award, and the SIGPlan Software Award. So Shriram, thanks so much for being with us. Look forward to your talk.
Thank you for the invitation. I don't think this microphone is on yet. Yeah, no, it's fine. Okay. Yeah. People in the back, can you raise your hands, please? Good. That means the people in the back, are you reading your email or can you not hear me? Okay. You were reading your email. Okay, very good. Urj, thank you for the very kind introduction. ACM India, thank you for having me here. I know, as those of you in the know, it's been a bit complicated getting me here, so I especially appreciate your patience. We're going to start with some work. It's pretty noisy back here. Sorry, I can't hear the audience from here. Okay, good. So we're going to start with some work. I'm going to give you a little bit of homework. I'm going to give you a little problem, and you're going to yell out the answer. Okay? Yes, you're good? You're good with that? Okay. So I'm going to show you formulas, and you're going to tell me under what circumstances, for what values of A and B, are these Boolean formulas going to be true. Okay? Okay. So good, true, A and B are both true, yes, good. Okay, good. All right, here's another formula. So in fact, there seem to be how many solutions? 3 solutions, excellent. A is true, B is true, or A and B are true. Okay, good. You're getting warmed up. You know how this game is played. Okay, one more problem. There are no solutions, right? There are no solutions because you can't satisfy this. Okay, one last problem. Yeah, okay, good. So something like that, right? So what is the point here? This is the problem of Boolean satisfiability, okay? It's one of the classic famous problems in computer science, and this simple technique happens to have huge applicability because you can turn all kinds of interesting questions into Boolean satisfiability questions. So I and several other people have for many years built various kinds of tools for network analysis, security analysis, all kinds of other things, cryptographic protocol analysis. So touching on 2 of the speakers from today, the one before me and the one after me, you can encode those things into questions that can be solved by Boolean satisfiability. Okay? So it's a very, very broad topic. There is a problem. The problem, of course, is Stephen Cook and Leonid Levin's papers, right, which basically said these are, in fact, the canonical NP-complete problems, right? These are in fact, if you look at Cook's paper, SAT is literally the problem he used for reduction. So we can reduce many things to SAT, but in fact, all these things are very hard to solve, right? So this sounds like bad news, like I haven't actually helped you in any way. That is the mathematics. In contrast, there is the engineering, and the engineering is, in fact, we're doing very well. This graph is a little hard to read. You don't need to read the details. The point is, as time goes up, the size of the problem we can solve gets bigger and bigger and bigger. Okay? So we can solve large problems. We can solve practical problems. These things are now embedded in all kinds of settings. Okay? And in fact, the next edition of the next volume of Art of Computer Programming, actually the biggest section is on satisfiability. And what Knut says is the story of satisfiability is a tale of the triumph of software engineering blended with rich doses of beautiful mathematics. There's actually a third component. Anyone guess what the third component is? Software engineering, mathematics, and AI? No, 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 no. Even AI needs something to run on. Hardware, okay? So there's three things that have led to these graphs looking very, very nice. Okay? So that is satisfiability. I want to tell you about one particular perspective. I happen to be a big fan of this thing called alloy. It's presented in this book by Daniel Jackson and the rest of his team. And I want to give you a feel for what it's like to work with a system like alloy. And that will be the starting point from which we can talk about the research that I want to talk about today. Okay? So here's what alloy looks like. It looks a bit like an IDE. I don't want you to read all of the code on the board. I just want you to look at it and say, oh, it's got some curly braces. It looks a bit like Java code, right? Curly braces are good, right? Curly braces make us feel like code, right? So it looks like code. And what we've written here is a specification. We've written an idealized description of, in this case, a binary tree, okay? So we've tried to describe binary trees. And then we're going to ask, is this in fact a binary tree? By writing a property, okay? And in this property, we're saying that a binary tree means that it has a unique root node, okay? Now, the great thing about these tools like satisfiability solvers is you can translate this down into mathematics, and then you can click on a button over here. It's called execute, a run button, and it runs. It's kind of like writing a program in an IDE, right? You run this, and it's going to come back and say, well, actually, it's going to come back and say, not quite. Here's an example. Here's, in fact, a counter example, okay? Here's the counter example, right? Is that a binary tree? Why is it not a binary tree? Yeah. Any other reasons it's not a binary tree? So some people, for those of you who can't see, some people are doing this, right? There are loops. You can't have loops in a binary tree. Another reason, yes, is this, right? You have sinks rather than sources in your binary tree. So it's obviously not a binary tree, okay? So we have a nice concrete counterexample. So now let's say I go in and I make some changes, okay? I'm going to edit something, and I run the verifier again. It comes back and says, no counterexamples found, right? Great. Verification, at least for this one property, has succeeded. But the reason I'm excited about these solver technologies is because I can do something else that is very interesting, okay? The very interesting thing is, let's say I have the specification and I have not yet figured out what properties I want to check, okay? I'm still in the process of inductively building up my properties. Then I can just say, show me some examples of the specification, okay? And it comes back and it says, I found you some. In fact, I can click on the word instance and it comes up and says that. Is that a binary tree? Why is it not a binary tree? Well, this, right? This, there's also something else going wrong with it. Yeah, there's two things that are pointing to the same node, right? So the thing is, by looking at these concrete examples, we can start to infer, like, what are the ways in our spec is broken, and then turn those into properties, check them, and think of it as in an iterative process, right? So this is a very lightweight way of building up formal specifications. Some people call this lightweight formal methods, and it's a very powerful idea, okay? Now, that's the good news. Now I'm going to tell you about the human factors, right? So far, we've just been in the realm of mathematics and engineering. Now I want to talk about the human factors. I'm going to focus on 4 questions. What do we compute? What do we show? How do we show it? And how do we write these specifications? Those are the 4 areas I'm going to dive into, okay? We ready? We're good? We're good? Everybody with me so far? Excellent. Good. Okay, so let's start with what to compute, okay? So I told you that the underlying engine, the underlying technology is a satisfiability solver, right? I give it a formula, and it does what you did at the beginning of the talk. You were all satisfiability engines, right? You came back and said either it's not satisfiable or you gave me concrete instances, right? So the output that you get from these is a satisfying instance. That's all it is. Nothing more, nothing less, okay? That's the spec. We ask for one, we get that, And basically, we have these black box algorithms, and we get whatever the black box algorithm generates. Okay? That may not be exactly what we want. In fact, if you look at Jackson's book, he has the following text in there. He says, though the selection is arbitrary, in practice, the first instance generated tends to be a small one. And this is useful because small instances are often pathological and thus more likely to expose subtle problems. Okay? And I mean, it makes sense, right? If you think about it, if I give you some ginormous example, you might not see what's wrong. If I show you a nice small example, you're going to be like, yeah, okay, I see what's going on, right? Anytime you've written a proof, right, you've had your professor tell you, shrink it down, bring it down to its essence, bring things down to their essence. That's a good universal principle, okay? All right, so we did this. We built multiple systems that we call principled model finding, which is we try to have the output satisfy some stronger theorem, okay? And one example of this is a system called aluminum. And I'm sorry, there are going to be some very bad metal jokes in this talk, okay? So aluminum, because it computes the minimal models, okay? And then there was another system called amalgam, which tries to give you the provenance of models, whatever that is. We won't get into that very much today, okay? And this is like classic academic success, right? These were published, they were at major conferences, one of them won a Best Paper award. This is all great, okay? But I'm here to really tell you bad news. I'm here to tell you why my research was not very good, okay? Here's why my research was not very good. What happened is we started to look more closely at what we were saying. And if you read our papers, they say texts like, when given confronting scenarios, a user can be confident in something. Or an amalgam, it's crucial that tools empower users to do something, right? And anybody who's written an academic paper has written text like this. We all write text like this, right? Everyone's looking, in fact, all the theory people are looking a little guilty at this point, right? Yeah, of course, that's the first page, but nobody reads the first page. It's okay, all right? Okay, what if we take the first page of our paper seriously? Okay, what if they're not just fillers? So we wrote this other paper, and this paper did not win any awards, but it's far more important than the ones that did, because I think this has pointed me in a new direction for how to think about my research. So what we did was we said, let's take all these claims. So I told you about provenance, I told you about minimality. We took some other mathematical structures as well, and let's try to do some user studies on them. Okay, I'm sorry, we're having some font problems. The X just means a product. The box after it, you should ignore. It just means product. Okay, so we did it on multiple subjects. We did this with students. We did it with crowdsourcing audiences, et cetera. And there's actually a little trickiness there. How do you do like math logic with crowdsourcing participants? If you're interested in that question, talk to me afterwards. We did this with various domains as well. And here's an example that I don't have to explain very much, which is we're going to look at reference counting as a garbage collection technique, okay? Reference counting fails as a garbage collection technique because when you have cycles, it breaks down. It can't collect cycles, okay? So here is an example of the kind of graph that Alloy will produce, okay? And it's a pretty instructive graph because you can see that the heap is deeply connected, the heap has self-nodes, and that's going to cause your garbage collector to break down, okay? Yeah, except that's not what aluminum produces. Aluminum produces that. That's not of any use at all for our purposes, is it, right? That actually actively discourages you from understanding what is going wrong in this algorithm. Or here's another example. This is actually after a few steps, and you can see that there's an uncollected cycle sitting on the heap. The stack is pointing to a heap node that is not referencing those, and so those are going to just like leak memory in your program, okay? Again, minimal model looks like that, which again, takes away all the important information. So we did a whole bunch of these studies, and basically what came out was extremely depressing, okay? We found, first of all, that most of the students just dropped out of the study. Then they went back to using the default software, right? They didn't want any of this fancy principled model finding output, right? It just wasn't useful to them. They didn't like it. They actively disliked it, in fact. And what's worse is the students who did complete we did the same thing with the online participants as well, but this is with the student audiences. Basically, even when they did, they made all the wrong edits. So where they did use the tool, it actively misled them, okay? This was very sobering. And basically, we sort of realized that one of the problems here is we were chasing after mathematical elegance. And by the way, people in the audience were nodding along saying, yeah, minimal sounds like the right kind of thing. And there are some settings where it is in fact the right thing. There are other settings where it is exactly the worst possible thing, okay? So we said, okay, maybe we need to start judging our own claims a little harsher and think about what we're doing here by thinking about combining some of the human factors work that we could do with the mathematics and algorithmic work that we're doing, okay? So, and I will claim that our literature is full of these kinds of untested claims, and sort of one of my career goals is to start testing those and finding out which of those claims actually work for humans and which ones don't, okay? So that was the first part, like what are our algorithms going to compute? Next, what do we show them, okay? So our goal, you've seen some of these examples, right? You've seen some of these pictures. What is the goal here? The goal is we're going to show you some visual output that we're hoping will have some sort of effect on your brain that leads you to make the right conclusions and right decisions, right? That's our ultimate goal. That's why we show these visualizations, okay? Well, I mean, that's a deeply cognitive question, right? And we're not the first people to think about this. There are whole fields that think about this. And perhaps there's some inspiration we could be getting from all of these fields, right? There's actually a very, very rich literature, and I'm just showing you a sampling of some of the papers from this literature. So, you know, like Gibson and Gibson is like a seminal paper from the 50s that set off the field of like visual perception. And there's even work older than that. The paper on the top right is about the study of how do people identify the sex of a chicken, which turns out to be something you have to do a lot if you work on a farm. And it's actually a funny paper because the title doesn't say it, but the back half of the paper, it was written in 1987, which will help you understand why it does this. Also helps you identify NATO tanks versus Warsaw Pact tanks. Okay, seriously important questions. Okay, anyway, so the point is there's a literature that spans a whole bunch of areas, both from cognitive and perceptual psychology to educational psychology that tries to answer these questions. Okay, what I want to do is I want to walk you through an example. All right, so here's what we're going to do. We're going to talk about a society of blobs. We're not going to tell you which planet blobs are from. You're going to try to tell me something about blob society from the examples that I show you. Okay? We're good with that? Okay, so here is an example. So what it says is, this is a valid dinner party, and so you have two blobs. This arrow says cooking, this arrow says cooking, and this box down here says meal. Okay, what do you, so think for a moment and tell me, what do you infer about blob society from this picture? Anyone? Someone needs to be brave and tell me something. Come on. Once one person says something, other people will follow. They cook together. Okay, very good. They cook their own meal. Other comments, other thoughts? Sorry? They cook their meal at a party. Any other guesses? Too many cooks spoil the broth. Very good. I like it. You're awake. Okay. Other guesses? Other guesses? Okay. So there's some amount of information you've been able to extract from this picture. Notice these are all guesses, right? We're making conjectures. We don't fully understand blob society yet. This is similar to what happens when you take networking configurations or security configurations that you don't know and you're trying to pass it through an analyzer. You're going to get these instances and you're going to have to inductively infer properties about them because usually the sources are way too large to read and understand, okay? So we're doing this process of induction. Okay, so let me give you a second scenario, okay? So again, we have blob, blob, cooking, cooking, and meal, but we also have a parent-off relationship going from this blob to that. What does this suggest to you? Sorry? Parents teach their children to cook? Family dinner? Blobs are social. Yeah, it looks kind of antisocial in the top left, right? But it looks like they're actually maybe social creatures, right? Sorry? They are what? Yeah. Chef. Thank you. Excellent. Good. Okay, let me give you a third example, okay? But now I'm going to do something a little different. Remember, satisfiability solver gives you things that satisfy the formula. That's what you did, right? On the first slide, okay? Now I'm going to show you something that is not an instance of a blob dinner. Okay? It is a non-instance. This is not a valid party. I have blob, parent off, and cooking. Now, what might you guess from this? Does this add any information to you now? Children can't cook alone. Right? Well, why didn't you say that earlier? Because they weren't cooking alone, and also I didn't show you any non-instances, right? Like partly what negative instances do is they help us better understand the boundaries of a space, right? Yes? Oh, yeah, I'll fall at some point, and then you'll help me up, and it'll all be good. It'll wake them up when they start reading email. It'll wake them up by falling over. Thank you. Good, but no, thank you. I appreciate that. Yeah. Okay, good. So this presentation is entirely driven by reading the cog-sci literature. There's an entire area of what is called contrasting cases, and there are multiple principles that contrasting cases suggest. The main thing is it helps to show a collection of things rather than a singleton of things at a time, and especially if they are carefully chosen to contrast in some way. But the other thing you get out of the literature is that sometimes it may be useful to get and show negative examples, which is super weird if you think about it as a mathematician or computer scientist doing SAT solving, because we're saying, give me a thing that is a SAT unsolver or non-solver or something like that. Explicitly show me things that are not instances of the formula, okay? And yet, you're gaining insight from looking at the negative instances, okay? So this is one kind of study you can do. We call this a 2 plus 1 minus because on each screen you see 3 things. 2 of them are positive instances. 1 of them is a non-instance, a negative instance, okay? And you can guess that there might be other configurations to try. We probably tried it, okay? And this is again a situation where we have multiple sample domains, multiple conditions. We use crowdsourcing, we use student subjects, a whole collection of subjects to get at somewhat robust knowledge. And what we learned from this is actually that multiple instances are not always helpful, but negative instances seem to be, okay? And that's kind of weird if you think about it, right? There's a place where we want to construct non-instances from a SAT solver. And if you think about it, that's a really strange thing to do because there's an infinite number of non-instances, right? There's all kinds of garbage is not an instance of the specification. And so there's an interesting algorithmic question on how to construct non-instances that are somehow meaningful as opposed to garbage, right? And so this is a case where the cog-sci tells us a thing to study, the studies confirm that this is useful, and then we can go back and ask, what is the algorithmics that lets us generate those and study that question in a loop, okay? So if you're curious, I can tell you we generate what we call near-miss instances, right? So you take an instance and you tweak it in a little way. You do it by modifying formulas. If you're curious, ask me about it later, and I'm happy to talk about the math behind it, okay? All right. So what is the take? Oh, and by the way, the other interesting thing we learned is there's actually one mode that is even more effective than what I showed you. Have you ever had the situation where you're trying to understand something and you take 2 things and you put them like side by side and you flip them quickly and you try to look at the difference between them, right? Or you might like put things in 2 browser tabs, you go back and forth between the tabs or something like that. You flip back and forth quickly. You've had this experience, right? Sometimes kids' puzzles make you do this too, right? And that's what that situation is. You have 3 positive instances, but you can flip between a positive and negative by just clicking on a button, and it stays in place so you can see the differences. And that turned out to be the most effective mode of all of these, okay? So what are the takeaways from the second part of the talk? I'm going to claim that this is going to offend a whole bunch of people in the audience, but this is basically what we do as computer scientists, right? This is the wheel as designed by a computer scientist, right? Instead of trying to study the literature from other areas, instead of studying other domains, we sort of go off and invent a wheel and say, yeah, good enough, it'll probably be good, right? But we'll make these grandiose claims. And what I would like us to think about is if we could incorporate more methods into our research, if we break down some of these walls between theory and software engineering, algorithms, cognitive science, and so on, bring these in, we actually get to richer points, richer solutions, better solutions, more interesting places in space, okay? And our goal is ultimately, if it's to have a cognitive effect, in particular, there's a rich and relevant body of cognitive literature, just as there's a rich body of social literature if we want to have a sociological effect like in education and so on, okay? All right, third part of the talk, which is how to show things, okay? Once again, audience participation. I'm going to put up an instance, and you're going to tell me what part of computer science this comes from. All right? Yes? Ready? Okay. So here's the instance. Does anyone need me to read out some of the text? Can you read the text well enough? Okay, so I've got philosopher, philosopher, fork, right philosopher, next, left fork, right philosopher, left fork. Operating systems. Why did you say operating systems? Dining philosophers, right? Okay, good. And now I'm going to show you another state, okay, in the dining philosopher's algorithm. Can you tell me where all the differences are? Can you see the differences? Can you point? Yeah, you're pointing. Pointing where? Up, down, left, right. Right here? Oh, sorry, I'm not here. Yeah, where? Yeah, right about there. Yep. Any other differences? Somewhere over there? Yeah. Good. Okay. So you could imagine using this kind of thing to actually teach operating systems, right? Your textbook contains like a very static thing, doesn't let you experiment, doesn't let you try slight variations of dining philosophers. You could imagine giving this to students and having them try little variations and see for themselves how the algorithm works, right? Yes? Yes? Would you like to learn dining philosophers from these pictures? Really? No, not so much. Why not? A bit of a mess, right? Your brain's not going to process this. But isn't this how it's presented in your textbooks? Like this? No, how is it presented in textbooks? Yeah, everybody's drawing circles. Kind of like that, perhaps, right? And like that, right? So these are exactly the same states, exactly the same information. These is basically isomorphic. But what we've done is used a rendering that comes from the domain. And I think this one, I think we can agree, would actually be maybe a useful tool for a student to play with. Okay? All right, let me give you another domain, all right? So here's a picture. It says public key and ciphertext and yeah, some sort of RSA or it's a crypto protocol of some sort, right? I mean, it's obvious which crypto protocol, right, from the picture. Maybe not. But if I showed it like this, it's a lot clearer which protocol we're talking about. If you know crypto protocols, you'd recognize it. But it doesn't matter, right? What's going on here? The point is that various domains have spent a lot of time thinking about what notations make sense for them, right? They've evolved notations that make sense. Like some people like me call these Alice and Bob pictures, right? Message sequence charts, whatever you want to call them. The point is there's information conveyed here that's being lost over there, okay? So these pictures that I'm showing you are from our version of Alloy. It's a tool called Forge. And basically in Forge, you can do these custom visualizations, okay? It's actually not very much work, like 100, 200 lines of code will give you these custom visualizations for the most part, okay? But I want to point out that something's going on here that's more than just like pretty pictures, right? And to do that, I'm going to have to make you do some audience participation again, okay? So here's what's going to happen. I'm going to put some text on the board, on the screen, and you're going to tell me what color it is. Yes? We understand what we're doing? I want everybody to yell as quickly as possible, so you really have to put down your laptops at this moment, okay? I want everyone to yell. The moment you know the color, I want you to yell. Okay, you ready? 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 Okay. Too slow. Faster. Okay, what's going on? Okay, I played a classic trick on you. This is called a Stroop effect. Okay, and Stroop effect in psychology is basically, it measures the reaction time between congruent and incongruent stimuli. And what I just showed you, when I show you the text and the color in the same thing, that's a congruent stimulus. When I showed you in opposite ways, that's called an incongruent stimulus. And you saw for yourself what happens with incongruent stimuli. Okay? Now, why am I showing you this? Here's why. Let's take one last domain, okay? And I want you to see, so let me read out the text. It says farmer, fox, eats, chicken, eats, grain. What does this sound like? Yeah, there's a class, these riddles, they're called river crossing problems, right? Like I have to move the farmer, but the farmer eats something, blah, 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 right? Okay, good. Okay, so here is another presentation of it, okay? And we can agree it's kind of prettier, right? It's a cute looking chicken there. We certainly wouldn't want it to be harmed, okay? And now here's another pair of states after a change of state in the system, okay? The point is not just that the bottom pictures are prettier and maybe, like, oh, it's easier to tell which one's the chicken. The upper states, notice that they look isomorphic, right? Structurally, the fox and chicken are on the opposite sides the whole time, but they're on the same side of the picture, okay? And the farmer and the grain change sides, but they stay on the same side of the picture, right? Essentially, that picture is incongruent stimuli. It's a little bit like a Stroop effect on your brain being done by the tool, right? Now, the tool's not trying to go out of its way to mess with your brain. It's just like we have layout algorithms that try to do some things. In fact, this layout algorithm is actually trying to help you in some ways, and it's hurting you in other ways, right? So the broader point is not just, oh, we have cute, visualizations in different domains. The broader point here is there are actually important things about domains that a generic visualizer is not going to understand and that are very important for people to be able to understand what is going on, right? So not only have domains evolved metaphors, and sometimes we can even build sort of these epistemically closed systems for doing exploration of little domains, but also these spatial and temporal and other relations are critical for understanding the output that we see. And generic tools miss those, and so a large part of our effort in Forge is to make it as easy as possible to convey the spatiality and the temporality and other relations to the presentation system so that it can take those into account and use those when showing things to the user, right? So that we don't accidentally create Stroop effects on our users. Okay? Good. So that's the third part, and now I'm going to tell you the fourth and last part. Okay. How do we describe systems? So I'm going to focus on a very particular part of system description, which is a thing called linear temporal logic. Okay? Now, linear temporal logic starts with propositional logic, which all of you know. And how do I know that you know it? Because you've all done quizzes for me. You've shown me that you're SAT solvers, right? You're in the flesh SAT solvers. Okay? So you all know propositional logic already. But now let's say what I want to say about a system is I want to say something like, eventually I get a green traffic light, right? I'm looking at a traffic intersection. I want to talk about its properties. Or I never get the case that it's never the case that I get both a green and red at the same point, right? Like a safety property. Or I want to say something about like locks, right? That if you grab a lock, eventually you're going to release the lock. Or maybe, if you're like my household, you write down, your rules for your child, and and you write down like no cookies until you're done with homework, right? So there are all sorts of domains where we want to express these things, and you notice that all the words that I've underlined are statements about time. Okay? So in linear temporal logic, what you do is you extend propositional logic with these temporal operators. Okay? And if you look at like formal logic, they tend to use like single letter symbols. You can write them in single letters if you prefer, if it makes you feel like a little stronger or braver or something like that. But this is linear temporal logic. Okay? Now, this has been the source of a big battleground for many, many years. People who are old enough like me, and I think some others in the audience, will know that there were like these big battles, pitched battles about like CTL versus LTL and which temporal logic should we use. And people made decisions on this basis, right? So for example, here's Moshe Vardi saying, in contrast, the linear time framework is expressive and intuitive compared to CTL, okay? Or here's the temporal logic sugar, and it says we can easily and intuitively specify the designs. Now, you can guess that by this point, I'm looking at claims like this a little skeptically. Okay? In fact, the motivation for this work was LTL, which was designed for verification, has become very popular in robotic synthesis. Okay? So planning people have discovered LTL and used LTL in robot synthesis. And we went to a talk about robot synthesis LTL, and the speaker was from a robotics speaker, and so they did this very nice thing. They gave a brief tutorial about LTL at the beginning of the talk for everybody to make sure we're on the same page. And there was a mistake in the talk, and the speaker didn't catch it, and the audience didn't catch it, and made us think like, do people understand LTL? Let's go investigate a little bit. So what does it mean to understand LTL? Well, basically, you could break this down into two directions, right? I have something in LTL, and I want to translate to English. So if I read LTL, can I understand it in English properly, right? So I translate a formula into English. The other direction, of course, is English to LTL, right? And this is, in some sense, the thing we have to do on a daily basis. Well, but daily for my life, maybe not your life. But you want to write a spec, either for synthesizing a robot behavior or to verify a system. You have some natural language formulation in your head, and you have to accurately transcribe this into the logic, okay? So that is on the syntactic side. There's a subtlety here, which is there's also a semantics. The LTL semantics is given in terms of these infinite word automata. And so there's another thing you can do, which is also see whether people understand the semantics, which is called in terms of traces. Okay? And we did this lots of different, multiple years, multiple audiences. We even got data. This was fun. We also got data from people who are actually researchers who use LTL. Okay? So that was a very interesting data set that's not always easy to get. And what's interesting is what we found, it didn't really make a difference whether you were a student learning LTL or a researcher using LTL, which might disturb you at what's about to come. As you can guess, but in fact I'm giving this talk, it was pretty disastrous. And I want to focus on one of the problems that we found. So this was an attempt to systematically describe the problems that we found across these audiences and across years. And I'll give you one example of this, which is what we call the exclusive view. Okay, so I'm going to say X until Y. And I'm going to propose two different meanings for it, and you're going to vote for me, okay? You're going to tell me which one you prefer, right? So I don't want people to feel embarrassed by raising hands, so the way we're going to vote is we're going to hum, okay? So IETF style. So can you all hum for a moment? Come on, everyone. Even the professor is allowed to hum. Okay, good. Okay, so you all know how to hum, okay? So here are two choices. One is X is true until time t. At time t, Y becomes true. The second interpretation is the same as before, but at time t, X becomes false. Okay? All right, so you get to vote. How many of you vote for 1 by humming? Not a lot of people, okay? How many of you vote for 2? Were you all Americans? You don't vote? Ooh, yeah, okay. All right. Okay, let's try it again. 1. Okay, and 2? Much stronger for 2. Okay, good. Now, how did you choose? I mean, I'm asking you to pick a semantics for a logic here. How did you choose? You probably used like an English sentence and translated into your head and said like, which of these two behaviors do I get, right? And so let me give you an English sentence, all right? Here's a sentence. Robot's motor is on until the robot reaches its destination. Which semantics is this, 1 or 2? Which one would you want? You want 2? Why would you want 2? Because you want that, so you'd be very disappointed if the robot got there and kept running, right? You want the robot to shut off. Good? So there's a good intuitive reason for why we actually want 2, okay? Any LTL people in the room? I know there's at least one. What's the actual semantics? It's 1, okay? But let me make you not feel too bad about it. Let me give you another sentence. Which semantics is that? It's not committing to eating a cookie, right? So it's not actually saying the moment I clean my room, I will eat cookies. So it's actually a little closer to 1. Right? So you can start to see the kinds of issues you run into when you start to understand how people interpret logics, okay? And sort of a long story short, what we discovered is people actually generally did pretty well going from LTL to English. I showed you one of the main exceptions, okay? Trace satisfaction, the semantic level was pretty bad. And English to LTL, which is the most important one, right? Like that's the one you engage in the most. It's like really bad. Okay? Which is disturbing because that's the one we need the most. Okay? So what do we take away from this? First of all, there's all sorts of implications for the tools that we build, right? Because we build these tools assuming that people have perfectly stated their intent. But if people can't perfectly state their intent, maybe we should be adding more into our tool cycle to make sure that people's expressions are what they wanted to be, okay? Secondly, we've created a bunch of valid instruments that would be useful for teaching. So if you teach LTL, get in touch with me. If you teach any logics at all like this, get in touch with me. I'd be happy to share our instruments. You can improve your students' learning of these tools. But finally, I think maybe the most interesting thing to me is we have potentially better designs for these logics, but more importantly, we now have a methodology for how to go about designing a logic. So the next time you want to design a formal logic for verification, synthesis, something like that, instead of just writing these like bold statements about, oh, this will be more intuitive, this will be more clear, we can actually test these and then design something that we actually know is going to be and figure out how to like educate people to prevent them from falling into pitfalls, okay? All right, so that's the end of the technical part of my talk. Basically, I showed you 4 things. What do we compute, right? We have satisfiability in this particular case as an underlying algorithm. We tried to make richer and cleverer algorithms that were mathematically a lot of fun, but not so great for humans. There's a huge open area, but how do you design the algorithm that's actually going to get the best human consequences, okay? The second is, what do we show? I showed you how there's a very rich literature in cognitive science and educational psychology that can help us here and help us build better things to show, right? Specifically things like multiple instances and even more negative instances, which is sort of the antithesis of what a SAT solver normally generates. The third one is, how do we show it? And here I try to make a case for domain specialization, not only because experts recognize them and students need to learn them, but also because we want to avoid creating misconceptions in the minds of our users by not taking into account, for example, spatial and temporal relationships. And finally, I talked about how to describe systems. I gave a case study of LTL and showed how there's a lot for us to do in these things, these languages that we design, that we think are intuitive, that we believe are intuitive. There's a huge wide open space here that needs to be explored. Okay? There's a lot more here. One example is, how do we get people to appreciate the need for properties for formal verification? Another one is, there are rich type systems that are basically a form of human factor, a form of formal methods as well. How do we design these type systems? Also, how do we explain these advanced type systems? They're doing very sophisticated things in very interesting ways, and oftentimes they give us huge benefits like reducing, memory violations and therefore getting rid of segmentation faults and improving system security. But if you can't understand them, you can't use them. And how do we bring all these other tools we have to bear to do these? So this is the parts of my work that I'm not talking about, but I'd love to talk to people about more. Okay? So to wrap up, what I really hope I'm trying to make a case for is that we normally think of like algorithms as separate from software engineering, as separate from like education, as separate from all these other things. I want to claim they're not. There's this beautiful virtuous cycle we can get into. If we do it too late, it becomes vicious. But if we do it early, it's virtuous. And there's all of these things can talk to one another, inform one another. We can actually get to a much richer style of algorithmics if you think of it as like cognitively justified algorithms rather than algorithms that we just dreamt up, right? There are rich problems waiting out there. They're a little different from our current problems, but they're no less rich for that. In some sense, I feel like they're actually much more challenging, okay? So I want to make a case for this way of thinking about the world. I've told you about Forge, so if you're interested in formal methods, if you're teaching formal methods, love to talk to you about the tool and talk about where we could go with this. And finally, there's my contact information. If you want to reach out, you're more than welcome to reach out. And that's the end of my talk. And Viraj, I think I am well under target, so I have time for questions. Okay, I'm going to skip the third question because you've already got an answer for that, but I will talk about the first two. So the first part is about the imprecision of language. And I mean, in some sense, the whole game of computer science is moving from the imprecise to the precise, right? This is the computer science problem at some level, if you will, right? So, and that's tied to your acceptance criterion too, because if I don't know exactly what I meant, then how do I even know whether I got there or not, right? And my response to that, so these are extremely great observations, and I would argue that one part of it is, this is why we have a variety of methods, right? We don't only have quantitative methods, which are very good at measuring precise things, but we have qualitative methods, which are very good at giving us insight into situations where we don't have proper precision, we don't have complete precision, we can't just compute a p-value and go home, right? And that gives us nuance into what are people thinking and how do we shape things in the direction they're thinking. But getting back to the precision question, in some sense, the hope, and this is also not entirely accurate, the hope is that the user has something precise in their head, okay? But the reason I like these lightweight methods is that's not always true. If you go back to the very beginning of my talk, right, I said, show me some examples of binary trees without even a property, right? And you see this example, like, well, that's not a binary tree. Well, why not? Well, because I don't like that part of it. Well, you codify that. Then you see the next one is like, well, that's not a binary tree either, right? So we do this by induction, right? We're sort of in a Popperian universe. We do this by induction. We falsify things as we go along. And then we get to a point where we maybe, and this is where working with other people helps us, because they come in and say, well, I don't think that's quite right. I prefer to think of it this way, right? So we have to go from the imprecise to the precise in steps. And we won't know exactly when we're there unless we have a very precise thing to begin with, which we sometimes do. We have mathematical objects, right? We have a spec of the Ethernet or specifications of these various things that we can use, and when we get those, or a crypto protocol, right? There is mathematics. Sometimes we have math, sometimes we have formalization, and sometimes we don't. But the other part of it is figuring out the misconceptions that people have and helping them with their misconceptions, right? There's an entire body of literature on this as well, on trying to figure out how to unearth misconceptions and how to correct them. And I prefer to think of it that way. So I said with the LTL part, we have to think about the tools we build. The tools assume you got it right. And instead, maybe we can say, here, you wrote down the specification. Let me show you some sample scenarios, right? You might say, well, that's not, no. And if I know the kinds of misconceptions you have, I can use the misconceptions to drive the sample scenarios that I show you, because I think it's quite likely you think those and those are wrong. And you might say, oh, that looks good. You're like, oh, that's not what you wrote at all, right? And so we have to use these kinds of inductive, human-driven processes to try to get closer to the truth. Is that a reasonable answer? Great, thank you.
Hope you can hear me now. So, Shriram, in the dining philosopher's problem that you showed, the initial visualization was like a spaghetti graph, and your complaint was that there's no dinner table even in the picture. But if you are looking for reachability analysis, for example, then
Yes.
somebody would have preferred the first picture rather than the table. So it also depends on the ultimate goal that you have, right? So it's not that one visualization fits all. So somewhere you have to factor that in as to what is the ultimate purpose of this visualization.
That is a great point. So I'm going to push back a little bit in the following sense, okay? If you're doing a visualization, odds are you're trying to show something to a human. If I wanted to do reachability, the graph would just sit as a data structure internally, and I would just compute it and I'd be done, right? So now, it is the case that sometimes I want to show it to a user and say, try to trace through something. And I think that's why, we have an ancient principle from software engineering, right, which is the model view separation. And that's essentially what we're doing here, right? I've got a model of the dining philosophers, and I showed you one view, which is a default view. I showed you a second view. And again, if there's another language you want to speak, another visual language you want to speak, we should have tools that enable us to speak all these different visual languages. And in some sense, that is one of the driving forces behind Forge, this tool that I mentioned, is I don't want to pick for you. But I think many domains tend to have sort of a canonical visual language, right? In fact, many of the things that our students have built is also like, games, right? Like, baseball, which is like this inferior form of cricket that they play in the US, right? Sorry. So, baseball has this canonical presentation of diamonds. Or maybe you're doing a card game, and then we have this canonical visualization in terms of a deck, right? So there are those, but again, I don't want to be judgmental. And again, in some sense, once you study that visualization, you may find it's not very good for the purposes you had in mind. So very much an open-ended question. Okay? Thank you.
Hi,
Just one
Shriram.
more. I cut my talk short.
Hi, Shriram. So that's a wonderful talk.
Thank you.
Yeah, I can use many of the insights in my teaching as well. So just one thing, like you told that there's some insights about this learning itself from educational psychology and all. Similarly, like for example, if you see machine learning, well, how machine learns, for example, the technique that you talked about contrastive learning. It's a well-known technique in machine learning, right? So can we also take some techniques like how the machine learns? If we understand that, can we actually use those insights in this? But one can argue that actually machine learning is borrowing from how human learns.
Yeah, I
and
think
all.
it's very much in that
But-
direction.
yeah.
I don't know enough to know the answer. I mean, at a generic level, I'll say yes, of course. We should certainly try to borrow techniques in any direction we can. We should try. I'm willing to try almost any reasonable hypothesis. So far, my sense is a lot of the machine learning ideas have really been like take a human learning insight and try
so
to.
I still want to
yeah,
hear to you.
Yeah, but yeah, I think it's perfectly reasonable. And if there's a radical new way that machines learn that we think makes at least some sense of the cognitive architecture, it certainly makes sense to try that.
Sure,
Yeah.
thanks.
Thank you. Last question. Make it quick. Otherwise, he's going to yell at me. Yeah.
Yeah. So, a lot of this really boils down to, there's a certain vocabulary in which we understand something best, and what we're trying to do is in different vocabulary. And we're trying to do this vocabulary translation.
That's right.
Large language models seem to be doing quite well for at least some aspects of this, particularly for teaching logic, for making real engineers try to use logic for specifying. Do you think that there's room there?
No, I think, look, we can't talk about computer science in 2024 without LLMs coming in, right? It's like it's a Godwin's law kind of thing for CS. So yes, the short answer is, of course, currently I've tried these things. They're not very good for now. But I think, again, we should go back to, your original question. We're trying to go from the informal to the formal, right? And so I think it makes absolute sense to think about tools like LLMs being in the middle. For example, you start by writing your property in English, feeding it to an LLM, getting it to generate the logic, and then working within the logic to try to tweak it. But I think the trick is figuring out what are the right tools to get into that feedback loop after you've obtained your first LTL formula, whether it came from an LLM or human or something else, right? To me, that's the interesting question. But if there's a way we can accelerate getting into that loop, right, to get from that informal LLMs or whatever, absolutely. People have tried to do this with like drop-down menus and various other things as well in the past. I'm open to any of those. The intellectually interesting questions to me that sit at the intersection of cognition and mathematics is, once we have that first thing, what does that loop look like? So, yeah. Okay, and now you really are kicking me off. Thank you very much.
Thank you so much. Please join me in thanking Shriram for the wonderful talk. Shriram, so is this on? So at ACM India, we thank our speakers in this way. We plant a tree in your name. We have a tie-up with an organization called 14 Trees. I'm going to invite Professor Meenakshi D'Souza to hand over your certificate, which has a QR code so that you can watch your tree grow. Yeah? So.